Hi, and hope you are doing well. I'm Jadi, and today I was doing some task which was very fun, kind of a security thing, and thought it's nice to share the general method with you guys. I was checking system calls to make sure a program is doing what it claims to do, but thought it's very fun to show you the method. Also, we can have a quick chat about how Linux kernel works internally and in general what a operating system does. Technically, when you run a command in Linux, what actually happens behind the scenes is very, very interesting. Kernel should manage lots of things to run a command. More than that, to run your computer, your GUI, your different programs, and everything. The Linux kernel, as any other kernel, is the core of our operating system. It is what stands between your apps and your hardware. It's a bridge between hardware and software. If I want to show you as a schematic, I can draw you the kernel. This is Linux kernel. You have some hardware here. Let it be your memory, your CPU, your hard disk, and other stuff, network card, many other things, screen, output, input, whatever you have, mouse, keyboard, whatever. And you have some programs you need here. For example, in this case, I'm running a presentation tool in my terminal here. I have an OBS running, which records the screen. I have another terminal here. I have another browser behind this terminal. I will show it later. And lots and lots and lots of at least 100 other processes just to run the operating system. My kernel should manage all of this, should give each of these share time of the CPU. Technically, you can't run them in parallel. In reality, they are running very fast alongside each other. If this needs some memory, it will ask for memory from the kernel. It says, I need 10 megabytes of memory. Kernel goes to the memory. If this is my memory, allocates this section, gives it back this section. So it can use it like a virtual memory. If they want to write to a file, same thing happens. They will ask for a file, they will write on it, but everything goes through kernel. This is a monolithic kernel design, which Linux is. There are other types like microkernels and other stuff, but in our case, this is what kernel does. This is called user space. This is called kernel space. Whatever is happening in kernel space is much more important, higher privileged, controlled by the kernel, higher access roles, and these kind of stuff. Whatever happens in user space has lower, not in a bad meaning, but should go through kernel to do what it needs to do. I have a chart here, prepared one from Wikipedia. This is from the user space and kernel space Wikipedia page. You can study it, but this is what happens behind the scene in a kernel. If you want to write your own kernel, as we were making fun of one of the tries, it is not a bad thing. If you are doing it to learn, to study, to educate yourself, or to do something amazing. But you should not brag about it when you started it. You cannot say, I'm going to write something which is better than Windows, Linux, and Mac and everything, or combine them in one. But when a PC runs, a bootloader hands over the execution to your kernel. This is your small kernel. It may just write hello world on the screen and die. Still an operating system, but a boring one. If you want to add to it, you have to be able to run another executable. For example, elf executable. You can say, okay, load, then a prompt. If a user typed something, try to read the disk, load this, and execute it. When it's finished, return back to kernel this prompt. You will have something like a old school DOS program. If you want to go further, you have to be able to run things in parallel. You can run different things in parallel. Support more and more what is it called? Support more and more file systems. You should go further than, for example, FAT, and start to grow your operating system. In some place, you will have an operating system which is much better. It will understand different file system. It can run files in parallel. It can access the network, but still it's not very useful because you should develop whatever you want, whatever needed on it. There is an amazing project called Holly OS, if I'm not wrong. Was it Holly OS? A guy with paranoia have done this. Temple OS, sorry. It's called Temple OS. A guy with paranoia, it was written by Holly C via using Holly C, amazing programming language. I may cover it once more, but many people just do to gather views. It's fun. I may do. Views are good. Tell your friends. Anyway, if you continue writing your own operating system like that, you will end up with something like Temple OS. The operating system which is super amazing for a one-person job, but useless in everyday life because you cannot, for example, use SSH on it unless you write your own SSH. We need user space programs like SSH, like GIMP, Bash, Firefox to be able to run on our operating system. So what should happen? One solution is first writing different modules like process scheduling so different processes can run, IPC so processes can speak with each other, memory management so you can dedicate parts of the memory to each process, virtual file system so programs will be able to write on disk, and networking. Okay, Holly OS have all of this, I think, except networking. He didn't believe in networking. At least God told him not to cover networking, if I'm not mistaken. Then you should let programs to speak with your operating system. That happens with system calls. You have to have different system calls. So if a program needs memory, they will call your mmap system call and you will provide the memory and return it back. If they wanted to write on a file, and Linux, everything is a file, so many different things would consider it as a file. But if they wanted to write on a file, they would call your write system call and you will answer back. Now, user mode programs are able to do useful things with your hardware, interact with your operating system. So these system calls are like gateways to your operating system, which is super cool. But now different programs should respect your system calls. As soon as you have these system calls, if you implement exactly these system calls, these 380 system calls, you will have a Unix-like operating system. So BSD, Mac OS, Linux, even to some extent Windows will have the same, at least same logic on Unix-like systems, exact same system calls. But it's very difficult to use this for actual work. Not very difficult, but these are difficult. We are low level. We are low level on a kernel mode. Hardware is here. To make things easier, different programming languages provide another layer here, which is called C standard library because it comes from C, old school C, and practically many programs do use them. Things that we know, like malloc, memory copy, what is local time, open a file. All of these are technically translated to equivalent system calls. Now, if you're writing a program with C standard library and you have C standard library on your operating system, regardless of what your operating system is, if you are using memcopy and you are on Linux, glibc will translate your memcopy to appropriate system calls on Linux kernel. Fun. Same program will run on Windows if your Windows do have a C standard library, which it has. if you're writing a program operating system called Temple OS and you provide C standard library, any standard program which is written on C standard library will run on your operating system, because C standard library will translate them to your operating system calls. Good thing about Unix is these are a standard. So all operating systems provide all of them, most of them at least, with based on a standard. So all Unix systems can work with each other. This is super cool. If you want to have a complete list, you can do a search for these system calls. You can search for Unix system calls. What I did? Linux. What? Linux system call table, for example. This one is nice. It's searchable, and all system calls are here. You can go through them, implement one by one, and you will end up with a Unix compatible system. There are 456 now. So, because these are for Linux, these are not standard Unix. Anyway, so this is how system works, layer by layer. On a higher level than this one, we have system components like your init daemons, SSHD, system daemons, your windowing systems like X11, which can draw a rectangular, which can show the mouse, understand where the mouse is, and this kind of stuff. And on a, not a higher, but another level is GTK, Qt, and others. When you are creating a graphical application, you can use Qt. Qt will work on X11. Qt is like create a window, create a button here, and input here. If I push this, do this here, and these kind of graphical things. GTK is the same, and many others. So your program like Mozilla Firefox, Blender, GIMP, or whatever you write, or Bash, a terminal, will use these. They will call C standard library. C standard library will call SysCalls to talk with the kernel. This is how an operating system works on a lower level. Today I was checking these system calls for the program. Sometimes you have this, you have a new program here, and they say run this on your server. This is a cool program. Your manager says, check it. What is this? And you go and check every single system call this program does. And you have a much better understanding if this program does what it says or not. You cannot have a final word, but you will have a much better understanding. This is also very cool in debugging and stuff. So this is how an operating system works. For scheduling and processes, here you have commands like top, which shows all the processes, what is running. This is my CPU, this is my memory this program is using. And PS will show you all the processes. You also have htop, which is a fancier version of top, CPU percentage, memory percentage of each program. You can click and say, show me the program with the most CPU incentive tasks. This is my memory, this much is used, what I did. These are my CPUs and whatever data you want. For the memory, you have things like FreeH, will show you how much memory you have, or you can go with cat proc mem info. Thanks to warp, it's here, it's cool. So you have different ideas, your memory total, memory free, and whatever is going on. This much memory is available at the moment, although this much is cached, so I can free this inactive memory and see lots and lots of different things. Things like, for example, dirty pages you have, the ones which you have not written yet, or other stuff. Anyway, this is cool. You can get lots of information here. Mapped. These are system calls with that M map we saw. Not one by one, but very, very related. But here I wanted to show you the system calls a program does. Let's go to a directory. checking. Let's create some files here. I can do an ls. It will show me the name of the files I just created with touch here. If I want to see what system calls ls does, there is a very cool command here called strace. You can do an strace ls. It traces all the system calls this program does, technically showing you on a very low level what system call is being called by the command you're using. Technically how this program is talking with kernel. So how it's accessing network, how it's accessing disk, how it's requesting for memory, when, which files, and technically you will understand the general behavior of a program. If you have a virus which does lots of access to other files, you will see it here. How it works. First, when you do strace ls, you are running ls, tracing all the system calls. It's not very difficult to read. This is the system call. These are parameters. So when starting, you can see exec this file. Cool. When you say exec, it calls a system call to execute something and sends this file on the disk to this system call. Then prepares some memory. Then accesses the preload libraries. When you're writing a program, you oftenly use different libraries. So this is my program. These are the libraries I'm using. For example, if I'm using ls, I might need to say lsa star. What does this star mean? I have to expand it. Is it like a regex? Or different things can use regexes. So you use a regex library. You may use a fancy printing library. You may use a networking library in different programs. So here, strace shows me that it accesses preload library to see if any preload library is there. The answer, this is the result of this system call, is -1. So no preloaded one. So it checks the cache of our libraries for the linker. Then maps something and closes it. You will see lots of things with this pattern. It opens a library, for example here, SE Linux. SE Linux is security enhanced Linux, does lots of security stuff on the accesses. So here I'm opening this library, shared object, so it's a library. I'm using a library, reading it, using it in memory and closing it. This will happen times and times with any executable you run. Technically now you can check what libraries this program uses. ls doesn't use much because it's ls and it should work without much dependencies. It needs libc, so it calls libc, again reads it, allocates memory and closes it. Then it goes to lib perl, maybe common regex system. So this is the one I was telling you. Opens it, reads it, puts it in memory and closes it. So it's loading all the libraries one by one. First it was the execution, then it was the loading the libraries. Then it goes to some system calls for threads. Prepares it for threads and protect, checks for limits. Every single of these is a system call in a Linux system. So you can check for this in your, for example, here there were all the searchable Linux system calls. You can go with this. I searched for this. Okay, here you can go to the direct kernel source where this is defined. I will show you later. So here I went here. Again, it checks the SE Linux, get random. Many of the programs will get random eventually somewhere because they want to do some security stuff. They need some random. Then it checks the proc file systems, because if it reads some data, it should understand the file systems. Then reads blah blah. Again checks the SE Linux. It's -1, so SE Linux is not being used. fstat memory. We are at the end, so let's have my pen. Some flags. Open at this. Now it reads the current directory with some flags. It gets back the data. Cool. Get dent S64. Not sure what this does. Let's search and we will learn, at least as a name. Even knowing the name is cool. And you will learn like this, step by step. Get directory entries. Cool. So here is the main part. It reads here, and then get directory entries, read the entries, closes. Now it has the entries. It needs a write system call. It writes 1, 2, 3, enter. The result is 8, maybe bytes, which is written or something. 2, so 1, 2, 3, 4, 5, 6, 7, 8. Yes, write returns the number of bytes written and then closes. Now you saw exactly step by step what this program does. So we know that ls is legit. It doesn't do anything extra on my kernel. It may do some calculations behind the scenes, but it's not calling kernel for any favors. It's not sending anything on the network or such. It was cool. The main part was here. It opened this, get directory entry, and then wrote these on the terminal. This was very nice. You can check these one by one. Here on the web, we checked it, but as you can see, this is like a manual page on Debian. What I can do is you can go with manual write. Here it shows you write, send a message to another user, because we are on write section 1. Section 1 of the write, I prefer to see them as different books. Book 1 is about executables. You can check that with a fun command, man. Check the manual of the manual. It shows you that there are different sections, or as I prefer, books. Book 1 is executable programs. Book 2 is system calls. Book 3 is library calls. Book 4 is special files. So we need the write from book 2 or section 2. So I will go with man to write. It gives me the write system call information. Write to a file descriptor, standard C library. It works like this: write fd buffer size, and it returns the size. Okay, this is cool. If I want to check the source, I can go to the Linux source code on Git. This is not where it is developed. This is kind of a mirror of the whole thing. So there are pull requests, so maybe this is not a mirror. I might be wrong. I don't know. Can I open a pull request? Don't know. I cannot remember. So here I can do a search for SysCall write. I cannot remember this. Don't know. Anyway, but I think Linux kernel is not being developed here. For sure the patches go through email, but I'm not sure because this is a pull request. Anyway, this is another story. Let's go for this one. System calls do use a macro, which is system call define. And there are different macros based on the number of the parameters. How many parameters we had? 1, 2, 3. So we need 3 write. Although it might have been, if you haven't know about this, you could browse the tree, go to fs, go to read write or open write or whatever it is called. Read write. This is it. It's defined here, as you can see. SysCall define tree. This is a macro which defines one of the system calls, write, and gets the same parameters. Easily, it just calls k syswrite. So let's check this one. On GitHub nowadays you can do this. So when you click on this one, it will show you where the more information is. This is defined here, referenced here. So defined once, referenced once. So we'll go to the definition. Definition is this one. Same file, Linux file system, read write. Nowadays Linux is very complicated because it should be able to run on lots and lots of architectures, on lots and lots of file systems. So this is not an easy call. If it was my own Unix-like operating system, I would just open a file and write into it and answer back, I did it. But it needs to understand about file systems, be able to run on different architectures and many things. So you will see this step by step checking everything, calling different things based on scenarios and such. So k syswrite. Technically it calls virtual file system write, what I was just telling you. It's defined in this file. Same file, a little bit upper previous. This looks cool. I think this is what is exactly happening. VFS write gets a file, gets the buffer, and most probably gets the size. Does some checks, verifies area for being RW, read and write. You should have access to write. Then it starts the write and it finishes the write. And then it writes it based on different criteria. For example, if this file has a write or this file has a write iterator. But at the end, it calls the writings. Very interesting. Now you're looking into the kernel, one of the system calls. This is more clear. But it's still very difficult to understand. If you want to understand, now you should understand what are these two and how are these called. For example, I have to go to this one, see where this is defined, why it's different than the other. New syscall, new sync write, sorry. This is sync writing, which should be easier. And you can go deeper and deeper, and any of them all are calling other things and such. So if you want to really start understanding Linux kernel, I have another slide for you. There are 3 books which can help you a lot. First, in this video, I just wanted to share with you mainly the strace and a good understanding of the Linux kernel and how it works. But if you want to go further, Linux kernel development is a very good book by Robert Love. This is what I have seen that many people point to when they want to tell you how to understand this. Understanding Linux kernel from orally is very nice, and there is something which is called a heavily commented Linux kernel. This is a very, very, very old version of a kernel, but heavily commented. Technically, each line has a comment at this one line. Most of the cases, more than one line, each part. So it's very easy to read. And also, if you want to understand how an engine works of a car, you cannot just lift up a hood, watch and see how this works. It's very difficult. It would be much, much, much easier if you could go 100 years back, check an engine. Much easier to understand. Then go forward 10 years. Go forward 10 years. That would be much easier. Same thing happens with this book, a heavily commented Linux kernel. I think a Chinese guy, long time ago, commented all the lines and told us what it does. And it's a very old version, so it's much easier to understand. You will have a holistic understanding after reviewing it, and you can switch to the newer books. Also, understanding the Linux kernel from orally is very nicely explained, and Linux kernel development is what people talk about nowadays. If you're here, I would be happy if you follow me, tell your friends about this. I will continue creating these videos even if you don't follow and you don't tell your friends, but that will make me more encouraged. Like, and tell me, I was thinking about maybe writing a small kernel module to show you how it works, or describe scheduling methodologies, maybe, or something else. You tell me. Have fun. I was Jody and still Jody.